Hello everyone. Today I will talk about time-contrastive network self-supervision learning from videos. And what is the motivation of this video? This paper is to learn a deep learning embedding for an image, which will map to images to 32-dimensional vector, and that embedding would be invariant to view, so different view angles should give the same results, different agents should give the same results, scale should give the same results, and background and orientation should be invariant. So this is our main motivation.
So a scale means that you can change the camera in and out. Agent can be robot or
human or different humans,
okay,
etc. So they capture multi-view from different angles. So you can see how they capture it. First person view generally a little bit stationary. Third person moves around to capture more different view angles, and it also gains some blur, etc. So those kind of effects, it also background changes. So those kind of effects are added to dataset. So how they use that two different views in their network. So they have view 1 and view 2. So they have view 1 and view 2, and then they select a frame in view 1 and call it anchor, and these two are synchronized and they select the same time from the second video and call it positive, and then select another frame from the first anchor sequence but in a different temporal time. So, and they call it negative, and they apply a triplet loss, which I will discuss later. Then they train their deep network and get their TCN embeddings, and from these embeddings, then they train their robot with RL network. So what is the triplet loss? So in the beginning, the red and blue, these two dots are closer to each other, and these two are more different than these two. But at the end of the training, we want that these two blue dots come closer and red dots should be pushed away.
So those two blue dots are one is anchored, the center one is anchored, the other blue dot is a positive.
Positive, and this is the negative. So if mathematically, if we express fx is our network's result, so the error or difference between two blue dots plus some constant should be always smaller than the difference between negative and anchor. And this should be valid for every possible triplet. And this is the main loss function for a batch size. So n means here for our batch size. If you don't have a multi-view video, we can still use this approach. Instead of selecting anchor and positive from different views, we can select from the same close sequences, and again negative is different time, and we can train our network with the same way. But the problem in here is these two, anchor and positive, is already too similar, so there is not much learning in here, but the learning comes from the difference between negative frame and anchor. So we don't get the multi-view invariant or background invariance, but we still learn what is the difference between those two frames. So what are their deep neural network structure? They start with inception model, and they take that inception model until mixed 5D layer, and they initialize that this model with pre-trained ImageNet weights, and this network gives a 2048 dimensional future vector. Then they apply two convolutional layers. After that, they apply a spatial softmax layer. Then they have a fully connected layer, and then they have embedding layer, which is another full connected layer with 32 units. And at the end of this network, we have 32-dimensional embedding vector. So they train their network with those two different images from different views. And after training this network, they use this network to capture embeddings from observation video. So they give robot only one video, and they take every embeddings for each frame. And also robot has its own camera, so robot can capture its own movements. And those movements also fed to the TCN network. And the robot tries to learn its own embeddings to match with observed video.
Okay, so let me just clarify here. So the can you go back to the go back? Keep going. Keep going. Yeah, this one. So here you see that there are two videos, and both videos are humans. But in general, one video can be human, and other video can be robot, and you can do the same thing. And so they're embedding with their learning, which will work for the robot example or the human example. And that's the main point here. And that's why the slide you were showing you, the last one, there you can apply this embedding basically feature vector, 30-dimensional feature vector, to do the coding in the robot. So, next one.
Yeah. To come automatically.
Okay, yeah. So as you see on the left, you can do coding, and human is doing that, but in the right, human is doing, but then robot is replicating that. So that's the very neat thing here.
Yes. So to measure their network quantitatively, they attributed 5 classes to their validation and their test data set. So these are not trained, these data sets are not trained with these attributes. So those attributes are: is hand in contact with container, is the container within pouring distance, what is the tilt angle, is the liquid flowing, or does the recipient contain liquid. So after they measured the after labeling their data sets, they measured how well performed their network. And random means here, it just selects one of the random attributes. So you can see it is almost 50%, and we have 4 different container angles, so it is 75%. And ImageNet inception is where they started their network initially. So it is ImageNet inception is almost the same with random. But after they trained their network with multi-view, they get really good results. And they compare with shuffle and learn, another self-supervised learning method, and it doesn't perform really well. And single view performs reasonably, but multi-view is the best way.
So these are the errors. These are the numbers. So smaller the better.
Yeah, smaller is the better. These are the error rates. So they have another metric for measuring the error. So classification error is the summarized version of it here from the previous slide. And alignment error is they give an observed video and try to find the nearest neighbors from another video frames. And if those 2 videos are aligned well, then that made a good job. And you can see that this is still an error, so you can see this TCN network performs pretty well.
Now about the training, the last column. This is the training iteration, right? Last one.
Yeah, so this is the training iterations. So actually they choose triplet loss function because of the training iteration. So they actually have another performance value, and in that graph it performed really well. So iterations are less iteration required for triplet. That's why they continued with that. So, like in here, this is the observed video, and this is another video. So they try to find the nearest neighbor frames. So you can see that it almost synchronized these two videos. So if this synchronization is perfect, then they achieved their intentions. So you can see multi-view, single view, and shuffle and learn compared with each other. These two are not flowing, so they are not really aligned, but multi-view does a better job aligning two different videos. So then they want to use their TCN network to pose imitation. So they started training their network with robot videos and human videos, but this robot video is random and humans are showing different poses randomly, so these are not synchronized. Then they give robot, and robot knows their internal joints. So with self-regression, robot learns its own its own internal joints. Then they again, self-regression, they train robot further with human supervision, but they say this doesn't, this helps very little. So, and this is a really expensive way of creating labels. So
just hold on, I think we'll change this slide. Okay, so just for understanding, can you back up a little bit? Okay, just I want to see the middle one. Yeah. So this is a very important point that now since they want to apply this method on robots, and robot is has joint angles. So if you change the joint angles, then robot will manipulate things. So here the middle one is given the picture of a robot. Then you want to come up with joint angles. So they train this regressor. For the training, they have a picture what the robot look like, and they have a joint angles because they can read from the robot. And they train the regressor, and then testing, you just have a picture, and then it will give you the angles. And then once you have angles, you ask the robot to do that pose. So that is being used here. Now it can be used for the when the human make a pose. Since this embedding has been learned, it will work for human or the robot. There's no difference. So which is an exciting thing. So the person will do the pose, and robot will, then that picture will go to the regressor, and regressor will give you the 8 joints. That will go to robot, and robot will make exactly same pose. So which is what they're doing.
So this is the whole network. So for this one, they added joints decoder, which decodes this 32-dimensional vector to robot's joints, and still this is not done by any human interference. Robot learned this decoder itself. Then when an observation video is given, robot can imitate those video. So what are those robot joint angles? They have 8 joint angles, and you can see the errors. Random is again random behavior, and so you can see if robot is only trained with human supervision, it doesn't perform well. But when their network TC is embedded, it performs really good. Only in shoulder pan, it performs really bad, and but when TC plus human and self is given, then it also performs well in that shoulder pan. And you can see there is very little difference between TC plus self and TC plus human. Also, we can see in this slide that human supervision sequences increases the robot joint angles distance error, but we still the TC plus self is performs better than only human supervised, and TC plus human plus self also the number of the human supervision sequences increases, the TC plus superhuman plus self performs well. And if they increase the unsupervised human pair sequences, which means that with different humans and they wear different clothes, so you can see that if the number of unsupervised human clothing increases, it helps to decrease the error. So this is a live video that robot watched this video and imitates that. So somehow robot learn an invariant map, like nonlinear map between human and robot, because human joint angles are really different than robot joint angles, but somehow they imitate well. And this is, you can see that nearest neighbor's third-person view is found from different videos, and you can see multi-view behaves, well, multi-view finds more similar videos from other frames. And again, it's the same in the robot pose imitation. So if they give this reference frame, it finds similar frames from other videos, and you can see it finds even the robot really close to this frame. So it means it learned also robot poses. And this is the TSNE colored by attributes, and you remember those 5 attributes they have done. So before training, these attributes are distributed randomly in the map, future map, but after the training you can see each color somehow clustered together, and this shows that their network learned these attributes.
So the idea is that each of these attributes corresponds to a particular image, and particular image is embedding 32-dimensional vector. So the 32-dimensional vector you can show in 2D using TSNE. And each dot in this thing is a particular image. And the colors are corresponding to different attributes. So if you look at the left, then they are all jumbled together. But after you embed it, which means each image has the 32-dimensional vector, which is curved, which is view invariant, and so on. Then the corresponding one, the colors cluster, which means head contact with container will be all those will be closer as compared to liquid is flowing. And these can be corresponding to the robot, person 1, person 2, person 3, as far as it's the same kind of attribute. So which is very good.
And also you can see this is the every color represents a different agent. That agent can be a human or a robot. And when they take from this cluster these frames, those frames look like each other. And when they take, for example, this cluster, these frames, they look like each other. And also you can see the robot also clustered at the same space. Also, when they colored by view, that this TSNA before training, view means they have 3 different angles where you perform the pose, and those poses are clustered according to view, you can see, because they started with ImageNet, so their starting network is already somehow trained, but it clusters according to view. But after training, you can see those clusters are distributed all over the place. So this shows that their network started to behave view invariant. Also, this is clustered by the agent, so every color represents a different agent. In the beginning, it is clustered according to agent, but after the training, all agents are distributed. So this shows also their network starts to behave agent invariant. So also they tested for orientation and scale invariance. So in here, they only trained their network with, from view angles 0, 60, and 120. But then they tested their network with 13, 90, and 150 degrees. Error increased a little bit, but still it performs really well. So this also shows it becomes viewpoint invariant. Also, they trained from a constant distance their videos, but when they come closer by half, their error a little bit increased, but still it is performing really well. So also their network becomes scale invariant. So you can see from these image sequences that also follows the human pose really well. And from different agents, it also follows it. You can see arms and shoulders. So how they trained their joint angles, or how they trained their robot? So they used a reward function, and it is squared Euclidean distance and Huber style laws. So V1 to VT is embedding frames of video demonstration that video which robot will imitate, and this is the embeddings of camera of robot, and the reward function is the difference between their embeddings and square root of constant plus embeddings. They use this square root because when W and V becomes really close to each other, the gradient becomes really small. But when you take derivative of this one, so this term goes 1 over some. This term comes 1 over something. So if this is small, then this is gradient becomes larger. So you can learn from. Still, you can learn better if the difference becomes really small. And so robot tries to fill the beads to another cup. So the maximum weight can be here, the green line. And you can see that the shuffle and learn or single view actually performs really bad. So they can't perform. But their network performs really well, and after 9 iterations, it reaches really good levels. In iteration 3, it still can't perform, but at iteration. So conclusion, with time-constrained networks, they showed they can learn a self-supervised understanding of the world and use it to learn real-world tasks entirely from third-person views of human. And that's all. Thank you for your time.